chapter 2 with just a few ideas, graphs or graphical. This is section 2.4, misrepresentations. Representations of data. And just, for example, what we call time series. This is an example. So I can present, let's say there is a nice, interesting example on life expectancy. Life expectancy. And let's say it's 60 and 70 and 80 years. And we can present, let's say, 1960, 1980, 2000, and 2020. And I can present something like showing that it really increases so much, so fast, like from 60 years old to, I don't know, a huge number. But actually, the graph should have been something like this. Which is for the same information, everything the same years, the same life expectancy. But this one shows a very acute, sharp increase. Because I want to say, oh, look, the life expectancy is so much, it increased so fast over the last 60 years. But it actually didn't. It went this way, a little bit, increase. So this is a misrepresentation. I'm showing you a sharp increase, but actually it's not a sharp increase. So in time series will be the first example. Misleading pie chart. I can manipulate the data and show something like this. And not correctly determine the angles as we did in class last week with percentages. So I would say this is 20%, and then I will write here that this is 15%. But as you see, the difference is, they should be maybe closer. Maybe I write here 40%, which it should not be 40%, because this, obviously, this angle is much smaller than this angle. So we can sort of manipulate data with pie charts. Also, what is called the 3D pie charts. Those are even worse, because you will see something like this, and it will be very difficult to determine, right? It's a 3D pie chart. So most of the time, the angle that is closer to us looks like it's bigger than all the other ones. Or it could. So these are normally not good for representing, correctly representing data. And in short, what are the guidelines for constructing good graphs so we don't give the impression that we are trying to manipulate the data or manipulate the results, basically? We should label and title axes clearly and present measurement units. So whatever I would like to present, let's say time from the moment a patient comes to an emergency room and blood pressure, I determine, or if I compare to another patient, I make sure that the measurement units are the same. The blood pressure is measured in the same way. I have the same increment for both graphs, especially if I want to compare. I don't have here 10 units and here I have every 15 units, because it will be difficult to compare. The same measurement unit, of course, and the same scale on the y-axis, because otherwise I will not be able to compare the two patients. avoid distortion, avoid clutter. In other words, don't present a lot of things in the background or sides of a graph, just these two, and compare them. Also the 3D charts, careful with that. We are trying to let the data speak for themselves. We organize it and summarize it, but we let them talk to us. And when comparing graphs, as I said, use the same scales, both sides, because you cannot compare apples to pears. So that's pretty much it that I wanted to say about 2.4. And now, if you have questions, if not, we'll start chapter 3. Any questions for me? Okay, so what did we cover so far? Number one, we talked about data. Oops, data. In the first chapter, we talked about data. What did we do in chapter 2? We summarize.
Professor?
Yes?
I had a question.
Please.
For the misinterpretation of data, there were a bunch of those examples in the homework. Do you want us to only know time series and pie graph?
If there is anything that you would like to discuss, I can share. It's a very good point. I can share. There is no way I can touch up on everything. You have to help me and say, let's look at this or let's look at that. I can share my screen. I can go to that particular example. That's fine. You just let me know.
I was just wondering if we only needed to know about the time series misinterpretations and the pie charts, because that would be nice.
Yeah, so the time series, so this is the idea. You have to be careful not to show or give it more interpretation. Just present the data so it talks to us without any input, without any bias. And for the pie charts and the 3D pie charts. But if you find some other examples, let's talk about them in class. So point out, let's say problem 2, section this, and I will share the screen. Please do. Anytime, okay? Everyone? Is that what you meant?
Yeah.
Okay, perfect. Please bring to class any questions, anything that you come across and we have not discussed it in class, because I want to discuss it in class for everyone. Okay, so in chapter 1, we looked at data. Quantitative, qualitative, etc. In chapter 2, we summarized it. Pie charts, bar graphs, frequency distribution, relative frequency distribution, histograms, right? Dot plots, stem and leaf plots. We summarized it because when we look at something like this, when I look at this, what's on page 2? When I look at this, what do I see? I have no idea. It doesn't mean anything to me. I can tell you that the lowest grade was 62 and the highest grade was 94, but I cannot tell you anything else. It's not summarized. It's not organized in any way. It doesn't mean anything to me other than the minimum and the maximum. Okay, now in chapter 3, we will start to analyze it. Analyze data. Oops. So we have the data. We collected it in, as let's say, simple random sample or some other valuable or correct scheme of collecting data. We know how to summarize it, so it speaks to us. And now we are ready to, after we summarize it, we are at the point in which we will start analyzing it. And the first section of this chapter, I'm hoping to cover 3.1 and 3.2 today. So in the first section, it talks about measures of central tendency. Central tendency. What is this all about? And I put it in parentheses here. It describes the typical value of a variable. The central, a typical value. So one measure, there are several. One measure of central tendency is the arithmetic mean, or the mean. This is number one. first of all, when do we use the mean? We normally use the mean to interpret the central tendency, which again is the typical value, normally for approximately or symmetric distributions. Yes, we will determine it for all distributions, but we use it to talk or present the central tendency normally for approximate or really symmetric distributions. What does it represent? It's the center of gravity, right? For quantitative data that is roughly symmetric. And now we do have two different notations. X bar, and that's how we read it, X bar, is for the sample, which a long time ago we said, which was 2 weeks ago, we said that the sample mean, the sample mean is called a statistic. Not a statistics, a statistic. Now we also have the notation which is mu, which is a Greek letter. It's the population mean, which in most cases we do not have it. And also we talked about that a long time ago, and this is called a parameter. And when we talked about it, about these two, we said this: the statistic will give us info, not exactly the parameter. It will not give us the exact parameter, info, or close to the parameter. That's why we want this to determine this. Now, before we move on, I want to present a notation. Very important notation. When we talk about a sum, we like to represent a sum by the letter S. However, we will not be using letter S to present the sum. We will use a Greek letter, which is also sum. It's still S, but it's a Greek letter, and here's the notation. Here's the way it looks. So this is still the sum. Why do we prefer this versus that? For many reasons, but this is one important reason. Because the top and the bottom will have some information. So the top and the bottom will have this information. So let me explain. Let's say I want to add 1 to 2 to 3 to ... 1,000. Here's another way of writing all this, because it's a sum. If it's not a sum, I cannot use the sum. If it's a product or anything else, I use other notation. For the product, you don't have to write this. We have the pi notation. So this is not important for us. We're not going to do a product. So we're going to only focus on the sum. So instead of writing all this, I know that this is the first element, x1, x sub 1 if you want. I see that this is the second element, like x sub 2, and so on and so forth, that this must be the thousandth element. So I will say this is the sum of xi. I'll explain what I represents, is the index. I is the index. And I goes from 1, the index 1 for the first element, till the index 1,000, from I equals 1 through 1,000. This is a condensed form of all this sum. Maybe it's a little bit squeezed in there, so let me give another example. Let's say we have 1 squared plus 2 squared plus ... plus, let's say, 20 squared. It's a sum of terms. So I'm going to write the sum notation, the summation notation, also called sigma notation. It's up to you, summation notation or sigma notation. How do I write this? So this is x, it's xi, it's squared, and from I equals 1 through 20. So this is, 1 is the lower limit, and 20 upper limit. Again, if I don't see this, I know that when I is 1, I have x1. When I is 2, I have x2. When I is 3, x3. Also, I have another way of presenting this. This is the general case. I didn't put the numbers in. So you can just write I squared from I equals 1 through 20. When I is 1, I have 1 squared. When I is 2, I have 2 squared. And plus, all the time, plus, because the sum. So we're not going to do anything with this. I just want you to understand. We're not going to work with or simplify the summation notation. All I want you to understand is what they present in the book or in your notes or everywhere else, something like this, it's not correct. It's not entirely correct. Or if they write like this, which we will write from I equals 1 through n. So there must be a lower limit, and must be an index, and must be an upper limit. So I'm going to write it in the correct notation. So I want you to have an idea of what this means. These being the general situations, and this is the case for I squared. Okay, enough of that. So now we can talk about the mean, because that was the discussion.